There are two concepts left that we want to discuss before we start graphing our trig functions, and those are the even and odd properties and the periodic properties. Now, the even and odd properties you should have heard about in algebra, but we will do a quick review just in case. And the periodic properties you probably have not heard about if you haven't taken some sort of trig in the past. So what we have here is, let's do a quick review from algebra about the even and odd. So even is the fancy word in mathematics where you have y-axis symmetry. Now, the most common function that we use to show y-axis symmetry is the function x squared, and it's the parabola that looks like this. Now, the reason that this has y-axis symmetry is because if I pick the x, for example, 2, well, 2 squared is 4, and if I pick the x negative 2, it is also 4. So every x on the left and the x on the right will have the same y value when they mirror each other. Now, mathematically, how we write that using function notation, and this is going to be important, is we have the f, when you plug in the x, right, this will output a y, but that will be the exact same y as when you input the negative x, okay? And so this is how you show y-axis symmetry algebraically. Now, origin symmetry, I'm sorry, is the fancy word for saying origin symmetry, and the most common function we use for this is x cubed, so it's going to be the function that looks like this. So for example, if we were to pick 2 here, not drawn to scale, then that will be 8. And if we pick negative 2, it won't be 8 anymore because when you cube, it stays negative. It will be negative 8. So what happens is it mirrors to the negative version of the point. So how do we write that mathematically? Well, what we say is that if you were to put in the negative of the x, it wouldn't give you back the same y. It would give you back the negative of the y. All right? So this is from algebra. This is a review from algebra, and then we use that into our functions. Now, of course, because we haven't graphed our functions yet, you might not visually be able to see that they're even and odd, but I'm going to try to explain to you why they are, which ones are odd and which ones are even. So here we have, oh, I see a little formatting error here, but it's okay. So the odd ones are going to be sine, cosecant, and tangent, and cotangent. So this little guy should be over here. Ooh, I don't know why he ran away. So what does that mean? Well, remember that if we look up here, odd, right, means that when we put in the negative version of the x, we get back the negative f of x. So visually here, right, it looks like the negative is being put to the front. It's not really what's happening, but if that helps you kind of understand algebraically what's happening. So we have the sine of negative theta will be negative sine of theta. The cosecant of negative theta will be negative cosecant theta. The tangent of negative theta will be negative tangent of theta. And the cotangent of negative theta will be negative cotangent of theta. Now the two that are even are cosine and secant. So remember that when it is even, right, whether you plug in the regular x or the negative x, it still comes back as the same y. So the cosine of negative theta is the cosine of theta, and the secant of negative theta is just the secant of theta. Now, why is that? So let's do a little visual representation. So if I draw an angle here, say I call this theta, my trig functions will be based on the terminal point right here. So I'll call this point A comma B, and say I am in a unit circle, so the radius is 1. Negative theta just means that you have done the same distance from the positive x-axis. However, you have done it in the clockwise direction. So the negative theta will be over here, right? On the unit circle, the point would be right here. But what is that point? Well, if you think about it, right, in terms of the x coordinate, the x is exactly the same, right? It's still A. So this is why, because cosine is the x value, this is why cosine stays the same. Whether you go counterclockwise or you go clockwise, the x is the same. However, what has happened to the b? Well, the b is no longer the same. If this was b here, now I've gone down, so this is negative b. So then I have negative b, and sine is the y. So sine becomes negative when you put in a negative theta. And of course, because tangent is sine over cosine, if one is negative and the other one stays positive, right, tangent will become negative. And the reciprocal ones just follow from their counterparts. Okay, let's talk about periodic before we put this to use. So here's a definition of the periodic property. I wrote the intuitive first definition. So what it means is that the graph or the y values have a pattern that repeats itself. Mathematically, it is the smallest p for period, such that x plus p is just the same thing as f of x. So you get back to where you started. Okay, I'm going to draw a diagram to kind of, I'm going to use the unit circle here. Let's just stick to blue. Why not? Okay, first of all, we need to remember that in a circle, right, you keep going around and around. That's a horrible circle. Poor little guy. We keep going around and around, right? So what happens is, let me put the axis points here. So we have 1, 0, 0, 1, -1, 0, and 0, -1. Okay, let's look at sine first. Sine is the y coordinate, okay? So I'm going to circle the y coordinate. I'd start at 0. Sine of 0 is 0. I then increase to 90 degrees, which is 1. The sine of 90 degrees is 1. I will then decrease back to 0. I will decrease even more to -1, and then I will go back to 0. Once I do this, right, the y values will start repeating themselves. So I will go to 0, increase to 1, decrease to 0, decrease to -1, increase to 0. So when do the y values start having a pattern? Well, after you have done a full revolution. So that would be 360 degrees. So after 360 degrees, the y values of the unit circle just keep going, repeating itself, right? Because you're going in a circle. So the sine, the period of sine is 2 pi. It's not smaller than that because if you look again, 0 to 1 to 0 to -1 to 0, the pattern here, right, there's no pattern that's smaller than that. So the period of sine is 2 pi. And because cosecant is the reciprocal of sine, it will also take 2 pi. So if you take a look right here in the table, sine and cosecant, right, they both have a period of 2 pi. So you can add or subtract 2 pi as much as you want, and it will give you the same exact ratio that you begin with. Cosine is the same, but of course with cosine you're looking at the x coordinate. So first you start at 1, and then you decrease to 0 for the x's, then you decrease even more to -1, then you increase to 0, and then you increase back to 1. So first you decrease all the way to -1, and then you increase all the way back to 0, to 1, I'm sorry. But again, how much did that take? That took 360 degrees. So the smallest period that cosine starts repeating its values is 2 pi. And because secant is its reciprocal counterpart, it also takes 2 pi. Now, I make a little note at the bottom there that I say sine, cosine, cosecant, and secant hold true just due to the coterminal angles. All right, just because it takes a full revolution of 360 and then you're back at the exact same spot. The ones that are a little bit different is actually tangent and cotangent, which they don't have a period of 2 pi, they have a smaller period. They have a period of pi. Now the reason for that is because tangent and cotangent are not just the x and the y coordinate, they're the ratio of the x and the y coordinate. So if I have my unit circle right here, and I pick a point on the unit circle, this is the point A comma B. Now directly across from this point, 180 degrees away, which would be the origin symmetry of that point, I would have the -a and the -b of it. All right? So if this would be theta, that means that this would be theta plus pi. And the tangent of theta would be the y coordinate over the x coordinate, sine over cosine. And the tangent of theta plus pi would be the negative b over the negative a, but when they're both negative, it becomes positive and it gives you the same exact value. So that means that this point here would have the same value as this point here. Then if you went a little bit further, this point would have the same value as this point. So the period is actually smaller and it is pi. Visually, this is going to be great. You're going to be able to see this when we actually do it, when we graph them. You're going to be able to see that the graph repeats itself. So hopefully that will help when we do it visually, because I know it can be a little bit hard to understand with the diagrams with the unit circle. Okay, so let's do an example. We want to find the exact value of the tangent of negative 37 pi over 4. Now there are actually a couple of methods. Now you can use whatever you want. You can use even and odd, periodic, reciprocal, coterminal, reference angle, everything we have learned, you can use it to find the exact value. So there are a couple of methods to do this. I'll show you two methods just to show you that now that you have so many tools, you don't always have to go one direction. I mean, sometimes there is only one way, but other times there are multiple ways. So method one would be first to use the even and odd properties. So tangent is odd, so I could put the negative in the front, quote unquote, right? That's not really what's happening, but it's the same. They're the same ratios, whether the negative is in the inside with the angle or whether the negative is on the outside. Now 37 pi over 4 is really large. It's much bigger than 2 pi. So 2 pi with a denominator of 4 is 8 pi over 4. So I can start subtracting some revolutions. And so I can see, okay, well, if I'm going to start subtracting multiples of 8, so it's 8, then 16, then 24, then 32, then 40. 32 is the one that I want to use because it's the one that will reduce the 37 the most. So I subtract 32 pi over 4. That's going to give me negative tangent of 5 pi over 4. But tangent has a period of pi. So if I want to, I can actually subtract pi from 5 pi over 4. I can only do that if it's tangent or cotangent. It's really important that you remember that, okay? Now pi is 4 pi over 4. So that's going to give me 5 pi over 4 minus 4 pi over 4 is pi over 4. I know that the tangent of pi over 4 is 1, so this is negative 1. Okay, so just to reiterate, right? The first one was because this is odd. This was coterminal angles. This was because of the period. And the last one is just because of the golden angles. Okay, we need to know the tangent of pi over 4 because pi over 4 is a golden angle. Okay, let's show another way. Method 2. Okay, I could begin by actually just doing the coterminal angles first. So instead of putting the negative on the outside, I could make negative 37 pi over 4 by adding enough 8 pi over 4s so that it becomes positive. So 2 pi is 8 pi over 4. So the biggest multiple of 8 that I need to add to make 37 positive will be 40 pi over 4. This is going to give me the tangent of 3 pi over 4. Now, I can't subtract pi from this because if I do, it's going to be negative again, and I don't want that. So this is in quadrant 2. Here I need to use reference angles. So 3 pi over 4 has a reference angle of pi over 4. It is in quadrant 2. So the tangent of pi over 4 is 1. In quadrant 2, it's negative. So the final answer is negative 1. Of course, it should give you the same. So here I actually use less. First, I only use coterminal angles, and then I use reference angle theorem. All right, let's do one more. In degrees, yay. So let's do the sine of negative 30 degrees. So, right, kind of, let's stick to the same colors. So kind of the same thing. First, I could use the odd. Sine is odd, so it would give me negative sine of 390 degrees. I could then subtract a full revolution, minus 360. That would give me negative sine of 30. 30 degrees is a golden angle. The sine of 30 degrees is 1/2, so this is negative 1/2. Done. Or I could do what we discussed and first make negative 390 degrees positive by using coterminal. I can't just add 360 because I would still be negative. So I'm going to add 720. That's going to give me the sine of 330 degrees. Now I can't make this any smaller because it's below 360. Sine has a period of 2 pi, so I can't take anything less. So I need to use reference angles. So 330 degrees has a reference angle of 30 degrees. It is in quadrant 4. So in quadrant 4, sine is negative. The sine of 30 is 1/2, so it's negative 1/2. So in this one, first I use the odd property, and then I use coterminal, and then I use the golden angles. In this one, first I use coterminal, and then I use reference angle. So there are multiple ways to do it, and I just wanted to show you some of the different ways.